Let us look at another very important concept. So we will gradually build towards that. But up till now, we have seen that if we have a system described in the frequency domain, then a system is completely described by its transfer function. A system is completely described by its transfer function. That's very important. That's why we represent the system by a box and just write the transfer function in it. We know everything about that system for this input and this output. That is very important. If we change the input or if we change the output, then we need a new transfer function. But for a particular input and output, we we know everything about the system only just by knowing its transfer function. That's a very important thing to know. And now if I ask you that this is in the frequency domain, this is in frequency, how if we try to represent the same system in the time domain? We need a box here. The input now in the time domain is obviously the inverse Laplace transform of x of s, and the inverse Laplace transform of the output is y of t. So what will be this thing? The inverse Laplace transform of the transfer function. The inverse Laplace transform of the transfer function h of s is h of t, and it has a special name, and this is known as the impulse response. Impulse response is the time domain equivalent of transfer function. So basically the impulse response and the transfer function are a transform pair. So if we know the impulse response of a system, we can very easily find the transfer function just by taking the Laplace transform of that. And this is how things are in the in the time domain. In the frequency domain, we know the output is equal to the input into the transfer function. Input into the transfer function. So the product of the input and the transfer function gives us the output. What is the case here? So how is output related to input in the time domain? So we have xt here, we have ht here. Is it a product? No. The product in the frequency domain is not the product in the time domain. Summation in the time domain is equal to summation in the frequency domain. But a product in the time domain is not a product in the frequency domain, and a product in the frequency domain is not a product in the time domain. This is something else. And now we want to find what that something else is. So it is something new. And let us try to represent that new operator with an asterisk sign. So ht asterisk with xt is when you get yt. And in the frequency domain, x of s, h of s, y of s, and the asterisk become product, multiplication. So this is easy. We have found it till now. What is this is of importance and of interest right now. What is this thing? So let me take you to a small ride. So let us say we have a system h of s with input x of s and we get the output y of s, I ask you a question. What if we apply an input of 1 in the frequency domain? The input is 1. What will be the output here? What should I write here? We know the output is the transfer function multiplied by the input. When the input is 1, obviously the output of the system we are going to get is the transfer function itself. Now I ask you, what is the inverse Laplace transform of this h of s? Is h of t. What is the inverse Laplace transform of 1? That is delta. What is this? You already know this guy. This is the impulse, unit impulse. So you see, when you apply a unit impulse in time domain to a system, the output that you get or the response you get for an impulse is the impulse response. So that is why the name is very logical. Impulse response is the output or the response of a system when the input is an impulse. So in the frequency domain, transfer function is the ratio of the output to the input, or in other way we can say the transfer function is the output of a system in the frequency domain when the input is 1. In the time domain, the output of the system when the input is an impulse is the impulse response, and the impulse response uh, is the inverse Laplace transform of the transfer function, or vice versa. The transfer function is the Laplace transform of the impulse response. You have to understand these concepts conceptually in your head. Obviously, we are not taking examples here. We are addressing to these new terms qualitatively. But this is very, very important. So I hope you understand this. If the input is 1 in the frequency domain, in time domain, it would be an impulse. And what is an impulse? You just apply something in zero time, for example, hitting something. So there is a football, and the footballer comes and hit it with it. So the football has been in contact with the foot for a very brief period of time, and that the application of the force to the football, where the foot transferred the energy to the football, was for a very brief period of time, that could have been modeled as an impulsive force. So that is the point of the impulse. So in a circuit, for example, we applied a very large voltage for a very small amount of time, or a very large current for a very small amount of time, is like we applying an impulsive voltage or current. So that's a very, very important thing. So now the question again is still there. What is this operator here? If we have 1, the output is h of s. If we have 2, the output is 2h of s. If we have 3, if we have 3 divided by s, the output is h of s into 3 by s. But what about here? If we have delta t is ht, if we have 2 delta t is 2 ht, that's right. But if we have say ut, what are we going to get here? That's important. That's what we need to find. So let us now look at another ride that I am going to take you to. What we want to find is this thing. We have a system. It has some impulse response. If the input is some function x of t, the output is something, say y of t. We need to understand what this y of t is. So suppose xt is some function, say this way. So this is xt versus t, and say we get the output to be, say, something like this. we need to find how is this yt related to ht and xt. That's the question. So let us begin with what we know. We know that if the input to a system is delta t impulse, the output would be the impulse response. It's logical to say this. What if the input is not impulse at the origin, but is a shifted impulse? The impulse is shifted to a new location on t-axis, say to delta. If this is the input, what are we going to get at the output? So input is shifted, the output would be shifted by the same amount as well. So this is an impulse at t is equal to 0. The output would be, say it is something like this, the impulse response. So if the input is a sudden application of voltage or current, the output is something like this. So input was only briefly applied at 0, but the output persisted for a longer time. This represents there is memory in the system. Now we have the impulse moved from 0 or delayed by lambda, then this output, the same output would be delayed by lambda. This is quite logical, understandable. We are going one step at a time. Now what is going to happen if I multiply this shifted impulse? So what is going to happen if I multiply this shifted impulse with a constant k? Obviously, we are going to get a k here as well. So instead of taking a random constant, I multiply this by the value of the function at lambda. So that is x lambda. This is a constant of value. It's not dependent, it's not a function. T is equal to lambda. It is the value of x at t equal to lambda. Is a value, so this value will just get multiplied here as well. So here this is a unit impulse. This is a unit impulse at 0, this is a unit impulse at this. The area under the unit impulse is unity 1. But here we are now talking about an impulse at lambda which is not unit impulse. It has an area under the curve of x lambda. So we get something that may be, so if x lambda is the value greater than 1, this is going to, if this is x, if this is ht, then we are going to get that constant times ht. So it may be, it may amplify. Okay, so now suppose we are interested of doing the same thing at different values of t. So lambda can be here, can be here, here, can be before this. So it takes up all the values of lambda. So we move lambda and to all the values possible, and then what we do, so for a different lambda and impulse at that location, we are still going to get such things depending upon the value of lambda. But what if we now sum all those values, sum all the values of lambda from minus infinity to plus infinity, that is, we integrate with respect to lambda, not t. So we change lambda from minus infinity, bring it all the point to lambda and sum them. This is what integration is. So we are going to get the summation, obviously, because this is a linear system. We are going to get summation at the output as well. And what is this thing? Pay close attention to what this is. When we take the lambda values of lambda from minus infinity to infinity and take the values of x, add those values of lambda and multiply by unit impulse, then you see, if we take lambda and come up here, then we see for all the possible values of lambda we are going to construct the input function xt itself. So what is this thing? This thing is xt. So basically this is a function of time that we are interested in, the same system. So this must be y of t, and this is what we are after. This is indeed what we are after. Try to know and learn that this yt by this argumentation and concept is equal to x lambda into h t minus lambda d lambda integrated for all values of lambda. This is what yt is. So this is how yt depends on xt and ht, is this way. And this is not a product. This is not multiplication, simple multiplication. This is much more than this. So try to comprehend this. I will show you a little deeper into the meaning of this thing. But for now, you have to appreciate that we have ultimately come up to an expression for yt and seen how yt depends on x and h. This complicated relationship is something that is represented by an asterisk and is called convolution. So this is convolution. xt and ht are convolved together to form yt. So in the frequency domain, when there is a product, in the time domain there is convolution. So we can write this whole thing as the convolution in the time domain between two functions. So in the general way, let us say y1 of t is one function and y2 of t is another function. Then their Laplace transform would be y1 of s into product y2 of s. So this is an important relationship as well for the table that we will be using in the exams. When there is multiplication in the Laplace domain, there is convolution in the time domain. And vice versa, when there is multiplication in the time domain, there is convolution in the frequency domain, but we are usually not going to encounter that. And this is how convolution is defined. So for two functions, say y1 and y2, or say f and g, two functions, and convolved together, by definition they are equal to an integral for all the values of a new variable, say lambda or k, does not matter, and take one of the, we can show this by the way, that whether we shift this one or this one is the same thing. So convolution is commutative. So either you represent like this, f of k into g of t minus k dk, or use lambda, is up to you. And sometime, or most of the time, we use tau here instead of k. Or we can write this as f of t minus k into g of k dk. Why are these two equal? Because we can prove this. Other people have proven it. We don't need to do it. Convolution is commutative. That is, f convolved with g is the same as g convolved with f. So this is a new concept that is very, very important to learn and understand about convolution. And convolution, and the other important thing that we have studied is the impulse response. Two important terms we have learned today: convolution in this video, convolution and impulse response. And if we combine with the previous video, we have learned about the poles and zeros, we have learned about the transfer function, and then we have learned about convolution and impulse response, and what's the relationship between transfer function and the impulse response. Transfer function describes a system completely in frequency domain. So we can complete this. A system is completely described by HFS in the frequency domain, whereas it is completely described by HT, or the impulse response, in time domain. What does this mean? It means, what does complete description means? It means, as I have described earlier, for a particular input, not by particular input I do not mean that we know what the input is, but by knowing where the input is to be applied and in what form, whether it's a voltage or a current. For a particular input, whether voltage or current, and a particular output, what is to be measured, what is to be observed, what is to be taken as output. For a particular input and output pair in the frequency domain, a transfer once we know the transfer function, we know everything about the circuit or the system, and we do not require to solve that circuit again and again to find the transfer function if we just change the value of the input. So that's important. And in the time domain, if we know about the impulse response of a system, of a circuit, for a particular input and output defined, then we know everything about that electric network. So it's completely described. So what would be our goal? Our goal when dealing with systems or circuits is to find their transfer function once, and then understand what various types of input would do in the how would they affect the output of that system. We will come to discuss this quite a lot up till the end of this course, and therefore this is a beginning lecture for a very important study that a student of circuit analysis must know before he is through circuit analysis. What is else there to be reminded is that when we are finding the transfer functions, then the initial conditions must be taken to be zero. So a capacitor in the circuit, or all the capacitors in the circuit and all the inductors in the circuit, must not be initially energized. And the energy of a capacitor is depicted by a voltage on it, and the energy of an inductor is depicted by a current on it, current through it. So therefore, none of the inductors should have an initial current through it, and none of the capacitors should have an initial voltage across it. So then if you solve the circuit in the frequency domain, you can get a transfer function. And if a question says find the impulse response, you can always find a transfer function and then apply the inverse Laplace transform to find the impulse response. And if you know the impulse response, somehow you can easily apply the Laplace transform to find the transfer function. And we will see that solving a circuit is easier in the frequency domain. That is why we usually find the transfer function, and then find the impulse response if required.